As far as implementing any finite difference algorithm this semester, this lecture is the most important. We're going to introduce a concept called the Yee grid, and we are going to approximate the derivatives in Maxwell's equations by placing our fields on this Yee grid. And this is very, very important to understand the Yee grid, the placement of the field components within the unit cell, and how the finite difference expressions are derived. It's a little bit crazy, but in fact numerically it's a lot more efficient and very elegant. So I'll introduce the Yee grid, then Maxwell's equations on the Yee grid, and then we're going to go through one at a time and of all 6 Maxwell's curl equations and approximate the derivatives, and we'll spend a bit of time doing that. Then once we have all those finite difference approximations, we're going to be ready to put Maxwell's equations into matrix form. Once we're there, we can discuss some other things like numerical dispersion. I'll very quickly show how to generalize this to fully anisotropic materials, but we're definitely not going to do that in this class, and show you some alternative grids. But for this class, we are just going to do ordinary isotropic materials. But actually, since we're incorporating a PML, in fact, we can have diagonally anisotropic materials. It's only when you would rotate the tensor of those anisotropic materials that the way we're going to formulate our codes, it couldn't handle it without generalizing. Here we go. This was invented by Kane Yee back in the 60s, so it is quite old, and it is still around, and it's very famously now called the Yee grid, as we'll learn. We talked about this before, but we can have a 3-dimensional grid, 2-dimensional grid, 1-dimensional grid, and each cell is a box, and each side can have a length, and those can be different. So the delta x, the delta y, and the delta z are called our grid resolution parameters, and they can be all different. We want them to be rather similar, that is numerically more sound and robust, but they can be different, and in fact in most of our programs they will be slightly different. So the most intuitive thing to do is to place all of the field components at a single point within each cell. So here, for example, we're locating EX, EY, EZ, HX, HY, HZ at the origin of the cell. Maybe we'd want to put it in the middle of the cell. It doesn't much matter, but this is probably the most intuitive. We were just to try this without thinking much about it, and this is called a co-located grid. And we are not going to use a co-located grid. Instead, we are going to stagger our field components throughout the unit cell. So what is drawn on this slide is one unit cell, but all of the different field components, despite being in the same unit cell, are at physically different positions. Notice the x component of the electric field is right on the x-axis, but offset from the origin by a half cell. Likewise, the EY component is along the y-axis, but offset from the origin by a half cell. And we can say the same thing about the EZ component. Then the x component of the magnetic field is in the YZ plane. Of course, it's still parallel to the z-axis, but it's not on the z-axis. It's in fact offset by a half cell in the y and z directions. And a similar argument for HY and HZ. And so this is the arrangement that Kane Yee suggested. I don't know if I have my history correct, but there's some very, very good numerical reasons to adapt this grid. I believe his sole reason in that paper was the elegant way which this lets you approximate the curl operations with finite differences. But in fact, it does some much more profound things for us, as we'll see. So I showed you a 3-dimensional cell. We can reduce that down to 2-dimensional cells for doing 2-dimensional analysis. And what you'll notice is there's 2 modes, and this shouldn't be a surprise to you now as we manipulate Maxwell's equations. Very often they separate into 2 distinct modes, and this is going to happen for 2D problems. But notice the three field components for what we'll call the E mode are in this top plane of the 3D cell, and then these bottom three components would describe the other mode, which we're going to call the H mode. And then we can reduce this again to a 1D model, and assuming we have isotropic materials, that is really modeling the same thing, and in fact we'd only have to solve one or the other for a one-dimensional grid. Two-dimensional grid, they're definitely different, and a 3D grid, we're back to really just having one possibility again. So here are the big reasons why we're using a Yee grid. And in fact, in my mind, the biggest one is number one here. Notice we've been formulating our algorithms and just looking at the curl equations and ignoring the dot equations, the divergence equations. Well, it turns out as long as we stagger our fields in this crazy way, the divergence equations are naturally satisfied. We don't have to worry about that. In fact, if we used a co-located grid, this wouldn't be the case. And when I first started doing finite difference method, I really had nobody to advise me differently. And I went ahead and did a co-located grid because I thought that was the easiest, most obvious thing to do. And it worked at first. I was just doing 2D simulations, and I moved to a TM polarized wave, and suddenly I was getting 300% reflection and crazy, crazy numbers. And I went through everything. I went through my code, I would say easily hundreds of times, looking for a little sign mistake or something, and everything was always right, always right. And at some point it occurred to me that this problem doesn't happen with finite difference time domain. And the only difference was the Yee grid, that I could tell how I was implementing it. And I dug deeper and figured out, yes, this is a property of the Yee grid. And as soon as I adopted that and did a finite difference frequency, everything worked, and everything's worked ever since. So that was a hard lesson to learn. So that's the biggest one in my mind. The next thing is the physical boundary conditions are satisfied. So this just means we can assign materials to different points in the grid and just not worry about it. Everything's going to come out of the math. Now, I think the original reason this was done is that it makes for a very elegant arrangement of the fields on the grid. And this helps us approximating finite differences. So let's look at this real quick. Let's say we're calculating the curl of the magnetic field around E sub z. So we have these two magnetic field components within the same unit cell. This blurred fuzzy one is in the previous unit cell. This other blurred fuzzy one is in the previous unit cell. So immediately adjacent to this E sub z component are all of the components of H needed to calculate the curl. And in fact, I could look at any electric field component and I immediately see that right next to it are all the magnetic field components necessary to calculate curl. Well, now let's calculate the curl of the electric field. And what we see is that curl the electric field around the magnetic field, and what we see is immediately adjacent to magnetic fields are the electric fields we need. So by staggering in this arrangement, all of the fields are encircling the other fields. And this ties into really why it's satisfying the divergence equations inherently. So it's elegant for writing our equations, it's divergence free, and the boundary conditions are satisfied. So there's a lot of reasons to adopt a Yee grid. Now there are some consequences. I don't want to call these drawbacks, but definitely some things we need to keep in mind now. And this all stems from the fact that all of the field components are at physically different positions. So this means if there's a wave has phase. Well, if the field components are in different positions, they will be out of phase. So even though it's the X, Y, and Z components of the electric field or magnetic field within the same cell, they're out of phase. So we can't immediately combine them. They're not immediately compatible. Also, if we have some kind of curved boundary or material interface, that could slice through the middle of one of our cells. And in fact, some of the components might be outside that material and other components on the inside. So the fact that they can be in different materials tells us we actually need to create different material arrays associated with each component of the electric and magnetic fields. Now we're going to define this so that the epsilon xx permittivity occurs at the exact same points as E sub x. The epsilon yy elements of the permittivity will exist at the same points as EY, and epsilon zz will be at the same points as E sub z. And as I mentioned, since the x, y, and z components of the electric field can be inside different materials, even if they're within the same cell, we actually need to create unique arrays for these three different epsilons. Now, if we visualize them to the screen, they would look very similar, but they might differ near their edges where one field component's inside material and another's not. And another consequence of the Yee grid is that we're going to get something called numerical dispersion. So a wave traveling through your grid is going to propagate slightly slower than a physical wave would. Well, this makes it look like air has a slightly higher refractive index than it should, and that can throw off your answers. And there's some ways we can compensate for that. Here we're just visualizing larger grids. It starts to get kind of confusing, but I drew a 2x2x2 three-dimensional grid and drew how all the field components encircle the others. And it gets kind of confusing, but in fact it's very elegant. And then I drew a 4x4 two-dimensional grid for the E mode. And we can still see the circle there where we have an electric field and then there's magnetic fields immediately encircling it. So just helping for visualization. Now here's probably the most important part of this lecture, and now we're going to approximate our finite differences, but we're going to locate the field components consistent with Yee's grid. So we're going to start with Maxwell's curl equations. Of course, we expand them out into the 6 coupled scalar equations, and this is no surprise from lecture 2 or 3 where we prepared Maxwell's equations. We've normalized the magnetic field here. We've assumed that our permeability and permittivity are diagonally anisotropic, and in fact the only reason we did that was to incorporate the PML, which needs to be diagonally anisotropic. So the first thing we'll do is we'll normalize the grid coordinates, and we're multiplying by k0. As we mentioned before, this is essentially dividing the physical dimensions by wavelength. So our dimensions end up unitless and on the order of 1 instead of 10 to the minus 6 for microns, or something really small or really large. So we divide by wavelength, and then everything's normalized and does not have units. When we do that, the k0 gets absorbed into those coordinates, and it drops from the version of Maxwell's equations that we write. So we have the y prime and z prime and x prime conveying our normalized grid coordinates, but there's no k0 here anymore. So in fact, Maxwell's equations look a little bit simpler. So here we go. We will grab the first of Maxwell's equations, and we have 2 spatial derivatives and then a magnetic field. We're going to call this the equation for h sub x. So it's the equation for h sub x, and then remember the rule that every term in a finite difference expression has to exist at the same point. Well, since this is the equation for h sub x, let's make sure all of our terms in our eventual finite difference equation exist at the same point as h sub x. Well, one thing we need to do is define the permeability, mu sub xx, to be at the same point as h sub x. That way this product makes sense. Okay, so we're going to assign mu xx right here at this point. And we mentioned this on a previous slide, so that shouldn't be any surprise. Now let's look at these derivatives. These are first order derivatives, so it's slope, rise over run. And we want to estimate now the derivative of the E sub z component in the y direction. So here we are, h sub z, or h sub x at this point, and we want to take the derivative in the y direction of the E sub z components. So it's going to be, if we want the derivative to exist at a midpoint, then we need to grab an electric field from the following cell over here. That way this h sub x is right at the midpoint between them, and we can use a central finite difference to approximate the derivative. Okay, slope. So it's going to be this electric field minus this electric field divided by the spacing. So the quick way I'll word that is the electric field from the next cell minus the electric field from the same cell as the h sub x we're talking about, divided by the spacing, delta x. So here is our finite difference approximation. The electric field from the next cell, notice the j plus 1, minus the electric field from the same cell, ijk indice, and ijk indice. So we've done it. We have approximated the derivative of the electric fields in the y direction, and if this is a central finite difference, which it is, then this term exists at the same point as h sub x. Very good. Next derivative. Now we want to take the derivative of the e sub y component in the z direction. We're still sitting at this point. We want to take the derivative in the z direction. So here's our two y's that surround h sub x. And again, we see it's the electric field from the next cell. In this case, it's the next cell in the z direction, minus the electric field in the same cell, divided by the spacing, delta z. So we have the electric field from the next cell, k plus 1, minus the electric field from the same cell, ijk. And if this is a central finite difference, which it is, it exists at the midpoint, which is right where hx is. So we've now converted this one of Maxwell's equations to a finite difference equation. And we've verified that every term in that finite difference equation exists at the same point in space. Next equation. Hopefully this will get very repetitive for you. We're going to call this the equation for hy. So that means we want all the terms to exist at the same point as hy. So we're going to make u sub yy exist at the same point as h sub y. So all terms in this equation better fall right where I have the laser pointer. Okay, so let's look at the first derivative. We want to take the derivative of e sub x in the z direction. So z direction, it's up and down. And since we want a central finite difference to give us an approximation that exists right here, we need the field values immediately surrounding it. Well, guess what? It's e sub x in the next cell in the z direction minus the electric field from the same cell divided by the spacing, delta z. So we have the electric field from the next cell, k plus 1, minus the electric field from the same cell, all over delta z. And if this is a central finite difference, which it is, it exists at the midpoint between those two, which is right here. Next derivative. The derivative of e sub z in the x direction. So let's come over here. We're taking a derivative in the x direction. We want electric fields surrounding it, so we grab these two. And we have the electric field from the next cell. In this case, it's the next cell in the x direction, minus the electric field from the same cell, divided by the spacing delta x. So here's the electric field from the next cell, minus the electric field from the same cell, divided by delta x. And this finite difference also exists at the same point as h sub y. So now we've converted this equation to finite difference form, and we've verified that every term in that expression exists at the same point. Next equation, h sub z. I'll go a little bit quicker now. We're going to call this equation the equation for h sub z. We will define u sub zz to be at the same point. And first we want to calculate the derivative of e sub y in the x direction. So let's come over here. E sub y in the x direction. So I'm traversing in the x direction here. It's going to be the electric field from the next cell minus the electric field from the same cell, divided by the spacing delta x. We have the electric field from the next cell, I plus 1, minus the electric field from the same cell, divided by delta x. And this central finite difference exists at the midpoint between these two electric fields, which is right where h sub z is. That's where we want it. Next derivative, the derivative of e sub x in the y direction. So y direction is now this. We grab the two e sub x components surrounding h sub z, and we have e sub x in the next cell, j plus 1, minus e sub x in the same cell, divided by the spacing delta y. E sub x in the next cell, minus e sub x in the same cell. And this is a central finite difference that exists at the midpoint, which is right here at h sub z. So our third equation, now in finite difference form, and we verified that every term exists at the same point. We're halfway there. So we've actually finished the first set where we had the curl of E equals j omega h. Now we're the curl of h equals j omega e, the second curl equation. So here's Maxwell's equation. We will call this the equation for E sub x. So we're going to define epsilon sub xx to exist at the same point, so there's no numerical issues there. And so right now we're talking about this point, halfway through the grid cell along the x-axis. Well, our first derivative, we want the derivative of h sub z in the y direction. So let's come over here. Here's the y direction, and immediately adjacent to it is h sub z. But now something a little bit different happens. If we look at the two h sub z's immediately surrounding e sub x, the one that's adjacent to it now is in the previous cell. When we were taking derivatives of the electric fields, we reached to the next cell. Now when we're taking derivatives of the magnetic fields, we're going to reach to the previous cell because that's what will be surrounding our electric fields. So now we have the magnetic field from the same cell minus the magnetic field from the previous cell divided by the spacing delta y. So magnetic field from the same cell minus the magnetic field from the previous cell divided by the spacing delta y. And this is a central finite difference, so it exists at its midpoint, which is right smack where E sub x is. Next derivative, we're taking the derivative of h sub y in the z direction. So let's come over where we're going to be calculating our finite difference. If we look at the magnetic field spanning that, again, we're going to reach to the previous cell, this time the previous cell in the z direction. So now we have magnetic field from the same cell minus the magnetic field from the previous cell divided by the spacing delta z. And that's what our finite difference is. The magnetic field from the same cell minus the magnetic field from the previous cell divided by the spacing delta z. And that exists at the midpoint, which is right here. So we converted our analytical equation to finite difference form and verified that each term exists at the same point. Only two more equations. Hopefully this is getting repetitive and you're seeing the pattern. We're going to call this next equation the equation for E sub y. So we're going to define epsilon yy to exist at the same points as EY. Our first derivative is h sub x in the z direction. Now we're sitting over here. So if we look at the field spanning, again, we're going to reach to the previous cell. And in this case, it's the magnetic field from the same cell minus the magnetic field from the previous cell, all divided by the spacing delta z. Magnetic field from the same cell minus the magnetic field from the previous cell divided by the spacing delta z. This next derivative, we want to take the derivative of h sub z in the x direction. So we're here, we look at the fields immediately spanning, and again we'll reach to the previous cell. We're going to take the magnetic field from the same cell minus the magnetic field from the previous cell divided by the spacing delta x. Let's go up here, magnetic field from the same cell minus the magnetic field from the previous cell divided by delta x. And so we converted this equation to finite difference form and verified each term exists at the same point. our last equation. And hopefully you're getting frustrated with me talking through these and you understand this. If not, please rewind and keep going through this till you'll see how I'm doing this. So our last equation is our equation for E sub z. So we will define epsilon sub zz to be at the same points as ez, so there's no numerical issues. Now let's look at our first derivative. Derivative of h sub y in the x direction. So our terms are going to exist right where I have the laser pointer. This is the x direction. And we see, it's again the magnetic field from the previous cell that's spanning it. So we're going to take the magnetic field from the same cell minus the magnetic field from the previous cell divided by the spacing delta x. Here's the magnetic field from the same cell, magnetic field from the previous cell divided by delta x. And our very last derivative is h sub x in the y direction. Again, we're calculating a finite difference right here. Here's the x direction, the field spanning it, h sub x's. We're still reaching to the previous unit cell now. Magnetic field from the same unit cell minus the magnetic field from the previous unit cell divided by the spacing delta x. And that's what we have. H sub x from the same cell, h sub x from the previous cell divided by delta y. And we converted this equation to finite difference form and verified that each term in the equation exists at the same point. So here's a summary of what we've done. We've started with the 6 equations on the left. We approximated all of the finite differences, and we arrived at all of the equations on the right. On the left, those are functions of physical positions x, y, z. On the right, we now have array indices I, j, and k. I will be the array index in the x direction, j is the array index in the y direction, k is the array index in the z direction. And those will be integers. So if we look at these equations, we can see that they're curl equations. They don't look a whole lot different than what we had before. But now we're using these finite differences. The fields are staggered, so it's a little bit different than the finite differences we talked about in the last lecture. But in fact, if we used a co-located grid, which were the derivatives we talked about last lecture, these equations would be much larger and much uglier. And in fact not as accurate because the finite differences would have to reach out farther into the grid. So we've done a very good thing here by adopting the Yee grid. I won't get a whole lot into it, but solving three-dimensional problems with finite difference frequency domain leads to extremely large matrices. This finite difference method that I'm showing you is very, very simple, but it's also very brute force, which is why it's simple. So it doesn't do a whole lot to make itself very efficient, and so when we move to 3D problems, it becomes very inefficient. And in fact, 3D problems are much better handled by unstructured grids and surface meshes and things like that, where the variational methods do that. Finite element, method of moments, boundary element, spectral elements. But anyway, so for 3D problems, we're going to assume that our structure is uniform in the z direction and that propagation is also restricted to the xy plane. When that happens, all of our z derivatives go to 0. So we list all 6 of our Maxwell's equations, and there were z derivatives here originally. They became 0, and we're left with these equations. Now it turns out, if we look at these equations, they've now decoupled into 2 independent modes. These 2 equations contain only hz, ex, and ey. And this third equation also contains hz and ex and y. So we'll group this equation with these 2, and we're going to call this the h mode. Then we take the other 3 equations and we call it the e mode. So while each of these 3 sets of equations are coupled amongst themselves, no equations from the h mode contain any terms from the e mode, and vice versa. So Maxwell's equations have decoupled into 2 independent sets of 3 equations. So in fact, given a device, we have to solve it twice now to know everything about it. One's for the H mode and one's for the E mode. And why we call them H and E mode will make sense in a little bit. So what we've done is take Maxwell's equations from analytical form, put them into finite difference form, and then also show that they decouple into two sets of equations for 2D problems. So each of those equations now has to be written once for every point in the grid. So if our grid contains 10 by 10 points, which is a very, very prohibitively small number of points, that's 100 points total. We had 6 finite difference equations, so we're going to end up with a set of 600 equations. So we want to put this in matrix form now. Just a reminder, if we have a function on a one-dimensional grid, let's say we're storing our electric fields on a one-dimensional grid, it makes sense we could store these in a one-dimensional array that we'll call a column vector. A little bit less obvious, if we have a 2D array, we raster through this, and we can still list them in a single file manner. And in fact, no matter how many dimensions we have, even if we had 3 dimensions, we can always raster through that 3 dimensions and list all of the elements in a single file array. That's how we're going to store our field values. And we have 3 of them for the electric fields, the X, Y, and Z components, and 3 for magnetic fields, the X, Y, and Z components. So in fact, we're going to have 6 arrays like this, 1 for each component. So from last lecture, once we store things in a column vector, we talked about these big square matrices that multiply those column vectors to do operations on that column vector. And the first one we did last time was a point-by-point multiplication. And in Maxwell's equations, that happens when you have an epsilon times E and also a mu times an H. So here's our point-by-point multiplication, epsilon times E. We're going to store all of our electric fields in a column vector. And if whatever's in here is correct, it must come out this way. Epsilon 1 times E1, epsilon 2 times E2, epsilon 3 times E3, and so on. So what does that look like? Well, at the first point, we should get an epsilon 1 times E1. And if we fill in that row, it's just an epsilon 1 in that first slot. The second element should be epsilon 2 times E2. That places an epsilon 2 in the second slot. And there shouldn't be any surprise to you after last lecture that, in fact, it's a diagonal matrix. I almost think of storing this in a column vector. So it starts off in a 2D array that we can draw an image to the screen and see our device. Then we'll reshape it into a column vector, but then we're going to insert that column vector down the diagonal of a matrix. So here's our matrix operator for doing the point-by-point multiplication with epsilon. That's very easy. That's one line of code in MATLAB to do that. So now we have our derivative operators. The first thing we're going to want to do is calculate the derivative of the electric fields in the x direction. And remember, we're always reaching forward when we take derivatives of the electric field. It's the electric field from the next cell minus the electric field from the same cell divided by the spacing. So how do we do this? We list all of our electric fields in a column vector, and we need to know how to fill in this matrix so that we would perform a derivative operation. So let's look at the first point. The electric field from the next cell in this case is going to be E sub 2, and the electric field from the same cell will be E sub 1. So that's an easy one. E2 minus E1 over delta x. Each one of these are going to have a 1 over delta x. So if you'll see, we just brought the 1 over delta x to the outside. So all we have to do is fill in the numbers in this matrix that would give us the E2 minus E1. So what does that look like? It looks like that. Remember, this first column is relation to E1, and that's a negative 1. Second column is relation to E2, which is a positive 1. So this gives us E2 minus E1 then everything's divided by delta x. So we filled in our first row. Second point will be E3 minus E2. They're going to keep going up by one index each time. So that's how we fill in the second row. And if we look, it's E3 minus E2, and of course everything will be divided by delta x. So let's go ahead and fill in the next two rows. Now the last row, we run into this boundary condition problem again. Our derivative will be the electric field from the next cell minus the electric field from the same cell. Well, in this case, the electric field from the next cell would be E sub 6. That doesn't exist. That's a boundary condition problem. Well, an easy thing to do is just to assume that it's 0. We called those Dirichlet boundary conditions last time. And so we just ignore that term, and we only have a minus 1 in here for the E5. So here's our derivative operator for calculating the derivative of the electric fields in the x direction for a one-dimensional grid. And we also use Dirichlet boundary conditions. Now let's look at the derivative of the magnetic fields in the x direction. So the magnetic fields now are different than the electric fields, because now we're going to say the magnetic field from the same cell minus the magnetic field from the previous cell. So if we want to calculate the derivative at the first point, we need to have h sub 1 minus h sub 0 from the previous cell, and h sub 0 doesn't exist. We're going to use just Dirichlet boundary conditions for now and make it 0. And so that's how we would fill in the first row. It's just a 1 in that first column corresponding to h1. The derivative at the next point is h2 minus h1. Same cell minus previous cell over delta x. So here's how we would fill in the row. We have an h2 minus an h1, and everything's over delta x. Go ahead and fill in all the rows. There's no boundary condition problem here in the last row because the magnetic fields are same cell minus previous. And since we're at the end of the grid, we don't have to reach to h6. That doesn't happen. So we only have the boundary condition problem at one point. Now notice this looks a little bit different than the derivative for the electric field, which had the positive ones running. The derivative for the electric field had the positive ones running down this upper diagonal and the negative ones going down the center diagonal. So they look a little bit different here, and that's because the E and H's are staggered, and we're actually calculating our finite differences a little bit differently. For the electric fields, we reach to the next cell. For the magnetic fields, we reach to the previous cell. And so they also have their boundary condition problems at the opposite sides of the grid. So we did Dirichlet boundary conditions. Another one that's really simple, and it should make sense we're going this direction, is a periodic boundary condition. We're going to treat everything as if it's periodic. Well, for this one-dimensional grid, if it really is periodic, and we only had 5 points, if we ever needed an E sub 6, if it really is periodic, and the field really does take on the same symmetry as the device it's in, then E sub 6 and E1 should be the same thing. And that we would call our periodic boundary condition. So in fact, for this last point where we're calculating the derivative and we need E sub 6, we did have a finite difference equation that said E sub 6 minus E sub 5, but we'll just say E sub 1 instead of E sub 5. Now our derivative operator looks like this. We still have the positive ones going down the upper diagonal, negative ones going down the center diagonal. Here, for some reason, because of the mood I was in, I guess I pulled in the delta x, but we could easily write that on the outside. But now we have a term sitting here that we didn't have before, and that's in the column relation to E1. And we're using E1 in place of E6. Because if everything's periodic, we should be able to do that. So now we've built in a whole second type of boundary condition, a periodic boundary condition. we can follow the same procedure and calculate derivative operators on two-dimensional grids. And this follows the same outline as we discussed last time, but now we have field components staggered on a Yee grid. So here's what the x and y derivatives look like for the E and H fields. So the D is derivative, the subscript is the direction we're taking the derivative, and the superscript means here we're taking the derivatives of electric fields, and with the H superscript we're taking derivatives of the magnetic fields. Just like before, these matrices are almost all zeros, so we're going to store them as sparse, and we'll get into how to do that. And just like before, when we did the x derivative operators, we had these intermittent boundary condition corrections. So now that we're in two dimensions, we don't really have a continuous row of positive ones. We have some corrections due to the boundary conditions that we put in there. And both the derivatives for both e's and h's have those. But since it's only two dimensions and our last dimension is y, we don't have any corrections here. We have two pure diagonals. Now for the x direction derivatives, the diagonals are right next to each other. But for the y direction, they're separated, and they're separated depending how large our grid is. If the width of our grid has big NX cells, that's how many columns we'll move over before we insert our second diagonal. And the derivative, we go down by rows, and we go down by big NX rows before we insert the second diagonal. But these are cool. There's only two diagonals to insert. So my algorithms, when I generate these, I go ahead and I insert the two diagonals, and then I go back and make the corrections to the x derivatives. Here's some example derivative operators for 4x4 grids, a little bit larger. So use these slides to benchmark your codes. Make sure that your algorithms produce these matrices exactly. And we're not going to do three-dimensional analysis in this class, but here's derivative operators on a 3x3x3 three-dimensional grid. More derivative operators on the same grid in the y direction now, and then in the z direction. So since z is the last dimension for a three-dimensional case, here we just have the pure diagonals. For the y derivatives, we had some corrections. And for the x directions, we had even more corrections. Now, this is very cool too, and this is going to save you a lot of work. Couple points before we get to this. There's the transpose operation, and essentially we re-express a matrix by swapping row and column indices, and that's called a transpose. Now in MATLAB, you can do it one of two ways. You can spell out transpose, or you can do a dot apostrophe. If you just have the apostrophe, it not only does the transpose, but it takes the complex conjugate of all your numbers. The dot transpose is just the ordinary transpose. So the Hermitian transpose can be spelled out C transpose, and that's what happens if you just do the apostrophe. Now, if you have only real numbers in here, then the apostrophe comes down to just an ordinary transpose, because the complex conjugate of a real number is still just that real number. All the complex conjugate does is swap the sign, the imaginary part. So here's the useful thing. The derivatives for the electric fields and the derivatives for the magnetic fields are related through this Hermitian, or the complex transpose. And in fact, all you have to do is construct the derivative operators for the electric fields, and you don't have to do it again. You can just readily calculate the same derivatives for the magnetic fields. So let's say we have the derivatives for the electric fields in the x direction. We will take the Hermitian transpose and make it negative. If we had the derivative for the electric fields in the y direction, we take the Hermitian transpose and make it negative. So the MATLAB commands for that are this. So in 2 lines of code, once we have the derivative operators constructed for the electric fields, in just 2 lines of code, now we have the derivative operators for the magnetic fields. That's very, very cool. It halves our work. So last lecture, we said, why can't we just multiply together two first-order derivative operators and get the second order? And we showed, because of the way we were doing our finite differences at the time, that that didn't work. Now we're on a Yee grid. Let's see what happens. So this top row is what happened before when we multiplied two of our first-order derivatives together. And we see that this is a correct finite difference formulation. However, we're reaching farther out into the grid. See, there's a 0 between the -2 and the 1s. We're reaching way across the grid, and we're losing a lot of resolution. It should look like this, which is what we constructed manually. Now let's see what happens on the Yee grid. We have a derivative for the electric fields in the x direction that looks like this. We have a derivative for the magnetic fields in the x direction that looks something like this. Now, if we multiply these two together, voila, we get a very, very efficient second-order derivative. So even more magic happens by adopting this Yee grid. So in one slide, this is what we did today. We started off with the 6 Maxwell's equations in analytical form. We approximated all the derivatives with finite differences, and we stayed consistent with the Yee grid. And then, using our matrix operator approach, now we can write these in matrix form this way. If we had 1,000 points on our grid, we would have to write each of these 6 equations 1,000 times. So this one equation, written 1,000 times, collected into matrix form, would be written this way. The E sub z is a column vector containing all of the E sub z components throughout the entire grid. The E sub y contains all of the E sub y components throughout the entire grid, of course reshaped into a 1D column vector. And H sub x is a column vector containing all the hx components across the entire grid. Well, the mu xx is doing a point-by-point multiplication with hx, so this is a big square matrix, but it's diagonal. We'll just take our permeability array that if we drew to the screen we could see our device and reshape it to a 1D array and insert it into the diagonal of a square matrix. These are derivative operators. They're banded matrices with 2 dominant diagonals, although we saw when we had periodic boundary conditions, numbers can appear off of those 2 diagonals. But these are essentially just banded matrices, and hopefully you have the idea of how to construct them. So this equation is written 1,000 times then, or however many points we have, and we get this. So this represents many, many equations throughout the entire grid. And I could say that for the whole thing. So here are Maxwell's equations now in matrix form. And this is even a higher level summary of what we did from the start of the course. Well, the first thing we did was assume no charges. This was the second or third lecture, and for waves that's a good approximation. We normalized the magnetic field. We normalized the grid and assumed just diagonal tensors. We approximated derivatives with finite differences, and we put them in matrix form. So in one slide we've spanned many lectures now. So the rest of this will be a little bit of side topics, but I do want to talk a bit about numerical dispersion. And we'll start with the dispersion relation for ordinary isotropic materials. So there's nothing numerical about this equation yet. A real material that's isotropic has to satisfy this dispersion relation. And what it really says is the magnitude of the wave vector is constant. So if we know 2 of the wave vectors, we can always calculate the third. Skipping a lot of math I don't want to get into, but we can put a wave traveling across our Yee grid and calculate a dispersion relation very similarly. And if we compare these 2 equations, we see that they look pretty similar. Now I wanted to write a C0 here, but we know that a wave traveling in the Yee grid travels just a little bit slower than the physical wave would. So I don't want to put C0 there, which would be the speed of light. I'm going to put a V there, which is the velocity of the wave but we know it's a little bit slower than the free space speed of light. We want those to be the same, but because of numerical troubles, they're not. So here's a visualization of what happens, and the numerical dispersion artifact is much more significant at lower grid resolution. The higher the grid resolution, the more this goes away. So if I was to draw an index ellipsoid, if you will, or a map of refractive index as a function of direction, for an ordinary material, that's the dashed blue line. So it's a perfect circle, which means whichever way the wave is going, it sees the same refractive index and everything's the same. However, in the Yee grid, this looks a little more square. And in fact, not only is this different than the physical wave would, which is bad, it's not even circle, so it depends on the direction the wave is going. A wave going this way is going to travel slower than a wave traveling along the diagonals. And in fact, that's a general conclusion with the Yee grid. Waves along the diagonals experience the least amount of numerical dispersion, which is maybe a little bit counterintuitive, because it seems like there'd be more numerical stuff happening. So we go back to the numerical dispersion relation and we solve for that velocity v. We know that v is a little bit slower than the speed of light by some constant gamma, which you don't quite know what it is yet. But we can figure it out. Since we know that v equals c naught over gamma, we can take this expression and put it in up here for v and solve for gamma. So here we actually have an equation to calculate that constant, which is sort of like the refractive index of the medium, and we can figure out how much the wave is going to artificially slow down. We would like gamma to be 1, but it's going to be more like something like 1.01, and it's going to slow the wave down just a little bit. So what do we do about it? The first thing we'll do is calculate gamma in a slightly simpler equation here. So we have k naught and n instead of the other constants that we had before. So k naught is the free space wave number. It's 2 pi divided by the free space wavelength. And our refractive index is the square root of mu times epsilon, the relative permeability times the relative permittivity. A slightly more useful form. Well, if our wave is slowing down artificially, and we don't want that, it makes a little bit of sense that the fix to this is to speed it up. So how do we speed it up? That by changing our relative permeability and permittivity across the entire grid. So we're going to build a device on a grid, and it's going to have some relative permeability and some relative permittivity, and these will be a function of position. They'll change throughout the grid. We'll just take those two grids and divide by this constant gamma that we just calculated. And we're going to end up with a slightly adjusted relative permeability, relative permittivity that will compensate for this numerical dispersion. A couple catches here. We can only compensate for dispersion in one direction. So we have to think, is there a dominant direction of the waves in your model? If so, that's the direction we would choose. If not, well, maybe we can just take an average and look at the dispersion for a wave traveling at an angle of 22.5 degrees, for example. Also, we can only compensate for dispersion for one choice of mu r and epsilon r that we use to calculate gamma. So if most of the energies in one particular material that has a relative permeability and permittivity, maybe we would use that. If the waves are going all over the place, maybe we use some kind of average across the grid for that. So for compensating for dispersion, we tend to choose average or dominant values for the parameters that go in for calculating that gamma. And so that's the story with dispersion. Now I want to show you very quickly, because this question always comes up and I always say, we'll handle it, or we won't handle it here, and I wave my hand. So I added a few slides just to give you a taste of what happens when you add and want to model fully anisotropic materials. So these equations on the left is what we've done in this lecture. Well, suppose we wanted to retain all the tensor components. And that's our equations on the right. What happens? What do we do different? So if we just looked at our previous finite difference equations, we can make a real quick guess and write these equations down. Well, now we need to ask our rule. Does every term in each one of these equations exist at the same point in space? Now let's see. Remember, we called this first equation the equation for h sub x. This finite difference, it exists at the midpoint at h sub x, and we remember that from when we were writing the finite difference on the E grid. This exists at the midpoint, same point as h sub x. Of course, h sub x exists where h sub x exists. But now what about these two terms? By definition on the Y grid, the h sub y does not exist at the same point as h sub x. And in fact, h sub z also does not exist at the same point as h sub x. So we have two troubled terms here that we have to handle. And in fact, we have a lot of troubled terms. We of course have these two troubled terms, but the only non-troubled terms on the right-hand side were the original diagonal terms that we retained. All the off-diagonal terms exist at different points, and we need to do something special to handle those. And in fact, what we're going to do is use an interpolation to do that. So here are the corrected version of Maxwell's equations. These first three terms remain unchanged from what we derived today. The second two are the off-diagonal terms, and it turns out we have to average from h sub y from 4 different positions, and we're going to average the product of mu xy times hy at 4 different points in order to interpolate it at the same point as h sub x. We're also going to interpolate the product of mu sub xz with hz at 4 different points, all surrounding h sub x, to interpolate it to exist where h sub x exists. And I make that argument for all the off-diagonal terms. So these are our corrected Maxwell's equations, a lot uglier here. Well, when we jump to matrix form, we recognize the terms we had from before, our derivative Ez, derivative Ey, mu xx times hx. And intuitively we would expect a mu xy multiplying hy, etc. But we're adding two other square matrices here, and these are matrices doing interpolations. Each one just interpolates along a single axis. This is interpolating along the x-axis, reaching backward to the previous cell. That's what the minus here means. This interpolates along the y-axis, reaching forward to the next cell. So the combination of these two interpolates along x and y, and that's why we have the 4 terms all averaged. Anyway, we do this for both sets of equations, and this is where we are. Our new Maxwell's equations in matrix form for fully anisotropic materials. We can write those in block matrix form, and things start looking a little bit more manageable now, but we still have these interpolation matrices in here. So in fact, this is what Maxwell's equations would look like, and the only difference is we've built in these interpolation matrices into the mu and epsilon matrices, which is neat and maybe a little bit surprising. And we can write it even more compactly in block matrix form this way. We can say a bold superscript E, meaning the curl of E. We'll put in our derivative operators this way, and we have the curl of E. And E is a bold E with a little vector, meaning it's a column vector of column vectors. This E sub x is a column vector. E sub y is a column vector, and E sub z is a column vector. So this is a column vector of column vectors. This is a tensor block matrix, and I put the little superscript capital R in it to remind us this has the rotation matrices built in. So really, this is the matrix form of our two curl equations, which is pretty neat. So what do the interpolation matrices look like? They look a lot like our derivative matrices. In fact, you can copy and paste your code that constructs those derivative operators, and in less than 20 seconds you can have the code for generating the interpolation matrices. So let's see what's happening. Our interpolation matrices, remember, only interpolate along one axis, and we multiply them together to do the 4-point interpolations. So our finite difference approximation, if we wanted to calculate the derivative at the midpoint between f1 and f2, we would use this finite difference approximation. Well, if we wanted to interpolate f at the midpoint instead of take the derivative, we would add the two together and divide by 2. So see the similarity here? All we're doing is we're changing this minus to a plus and the delta x to a 2. But other than that, everything's going to stay the same, including incorporating boundary conditions, where we insert the diagonals, etc. It all stays the same, just the minus becomes a plus and the delta x becomes a 2. So in the end, think of it this way. Think of your interpolation matrix that reaches to the next cell, interpolating in the x-axis, as sort of the derivative for electric fields in the x direction, but absolute value of that's what gets rid of the negative and makes it a positive. We're going to multiply by the delta x to get rid of the delta x from here, and then divide by 2 to divide by 2 for the interpolation. And so we can think of our two positive interpolation matrices this way. But strictly speaking, you don't want to do this. You want to copy and paste your code and create a whole new function for creating the interpolation matrices, because when we take the absolute value like that, we break whatever boundary conditions might be in there. So just like the derivative operators were related through the complex Hermitian, so are the interpolation matrices. And they're related this way, through the complex Hermitian, but there's no negative sign out here. Our derivatives were related with a negative sign out here. So essentially we only have to calculate 2 or 3 interpolation matrices, depending whether you're in 2 or 3 dimensions, and then we can calculate the other 2 or 3 immediately from them. So that helps reduce the amount of code you have to write. So that finishes the short answer on how you handle anisotropic materials. The last sort of bonus topic here is alternative grids. So let's remember 2 big drawbacks of our nice simple grid. It's real easy to work with, and it is very good, but it's not perfect. And one of the problems was the dispersion we talked about. But the other problem is it's square in a sense. And if we actually have a curved boundary, at some level we're going to have to make some kind of staircase approximation. So if we wanted a perfect circle in this Cartesian grid, we'd have to fill it in as best as we could to approximate the circle, but it's not perfect, and that's called a staircase approximation. If our cells are small enough, it's a pretty good approximation, but it's forcing us to use pretty high grid resolution, which will slow down our codes. Well, what could we do different? Well, one thing we can do on a structured grid like we're going to be using is we can use some dielectric averaging. We can just smooth the boundaries, if you will. That helps a lot, and we can do this. Well, the other thing that unstructured grids can do is they can perfectly conform to a circle so that there are no problems. And you'll also notice there's a lot less cells on the right in the unstructured grid than there is on the left. That's what buys you the computational efficiency. However, I'm able to teach finite difference frequency domain in, I'll say, 2-3 hour lectures. We would have to spend an entire semester, I think, to really treat finite element method or method of moments fairly. There's just a huge build-up to it. But one thing that some people do is, rather than have a square grid, is they will go with a hexagonal shaped Yee cell. And it's still a Yee cell because the fields are staggered, but it's in a hexagonal pattern. And in fact, that reduces the numerical dispersion. We still have some numerical dispersion, but it's less, and it's also more circular. The numerical dispersion is much more significant for large electromagnetic structures where your wave has to propagate a very, very far distance. that really exaggerates your numerical dispersion. Other people have adopted non-uniform grids, not only to combat dispersion, but to help conform to strange surfaces. Here's an example of a non-uniform grid, and this paper, I guess I don't have the reference here, but it showed that this was a lot more efficient. But what you can see is that we use a very sparse grid out here and a tighter grid where we're modeling, this is probably a microstrip line. So it's about a 50% memory and time savings by adopting a non-uniform grid, but the formulation and implementation is a little bit more difficult. We can also do a Y-grid with curvilinear coordinates. We actually bend them almost like spaghetti noodles. Even crazier in the formulation and implementation, but it can still be done, and people have done it. We can go to structured grids that have straight axes, but they're at oblique angles. And this works really well for those strange crystal symmetries that have oblique angles. This is a really good way of doing that. Otherwise, fitting these oblique angled types of devices into a Cartesian grid, there's staircase approximations and other crazy things that happen. And of course, I think the best overall, but certainly the most work and the most trouble, is an irregular, non-orthogonal, unstructured grid. And this has the benefits of everything. There's also certain cases where your devices have some kind of cylindrical symmetry, and in fact there's a Yi cell in cylindrical coordinates that make this type of analysis very efficient. And some example devices, if we have a waveguide bend, we can see here's the axis of our cylinder, so we could treat this as a 2D model but in cylindrical coordinates. Circular waveguides, fiber optics, dipole antennas are cylinders, cylindrical horn antennas, lenses are circles, and parabolic antennas, these are all circles and all things that are much more efficiently modeled using a body of revolution or a cylindrical type coordinate system. So that's it for this lecture. The key thing to come away with was how we took Maxwell's equations, we approximated all of the derivatives using finite differences, but placed the fields on a Yi grid. And the Yi grid let us implicitly satisfy the divergence equation so we don't have to handle it. Physical boundary conditions are handled, and it was a very elegant relationship to do finite differences. And we ended up with the smallest possible equations with the highest possible accuracy by staggering our fields that way. Then we took those finite difference expressions and wrote them in matrix form. And that's where we're going to pick up next time, and we're going to analyze waveguides. And then after that, we'll start formulating our finite difference frequency domain. So that's it for this lecture.